Hello there, this is Roshan Suresh Matthew and welcome back to the ANDS channel. In this video, we are going to demystify a crucial topic in the field of machine learning, hyperparameter tuning. Now if you ever wondered how to squeeze the best parameters out of your machine learning model, then you are in the right place. So let's understand what hyperparameter tuning is all about. Before moving forward, if you're new to this channel and like my content, please do leave a like and smash the subscribe button and turn on bell notification to stay updated for more interesting content. Stay tuned. Before we dive into the fascinating world of hyperparameter tuning, let's start with the basics and really grasp what hyperparameters are all about. Imagine you're setting out on a journey, and before you hit the road, you need to adjust your vehicle settings like the steering sensitivity, acceleration responsiveness, and braking power. These adjustments determine how your vehicle behaves on the road. Well, in the realm of machine learning, hyperparameters are quite similar. They are the equivalent of those settings for our machine learning models. Let's look at some of these settings and the effects the hyperparameters have on our model. Let's start with the learning rate. A high learning rate means a model will learn more quickly. It might also overshoot and miss the mark. On the other hand, a low learning rate ensures careful learning, but it may take longer to reach a destination of optimal performance. Next up is the batch size. This determines how many data samples we have to process at each time during each iteration of the training. Imagine trying to grant a handful of puzzle pieces versus the entire puzzle at once. A larger batch size might lead to a quicker convergence, but it requires more memory. A smaller batch size might need more iterations, but it could provide a smoother learning process. Then we have the regularization strength. It is like adding a little friction to the steering wheel, preventing our model from taking extreme turns that may lead to overfitting. Overfitting occurs when a model fits the training data too closely and struggles to generalize to the new data. So in essence, hyperparameters are a way of shaping how our model learns. They influence the rate of learning, the size of the steps taken, and the degree of constraints applied. Just as different drivers prefer different vehicle settings for the different road conditions, different datasets and problems require different hyperparameter choices to achieve its optimal model performance. Now that we understand what hyperparameters are, let's explore why they hold so much importance in the world of machine learning. Picture this. You are standing at a crossroad and you have two paths to choose from. Each path represents a different set of hyperparameters for our machine learning model. The choice of hyperparameters can be a deciding factor between a model that rapidly advances and thrives and the one that struggles to find its way or loses its grip. Take the learning rate for example. It's like adjusting the dial on a radio to find the clearest signal. If the learning rate is too high, the model might overshoot the optimal solution and keep bouncing around, never settling down. But if it's too low, processes might be sluggish, like turning the dial too slowly and barely tuning into the station. Now let's talk about the concept of overfitting. It's like a driver who's memorized every bump and curve of the neighborhood street but struggles to navigate in a new setting. In machine learning, a model that overfits learns the training data too precisely, losing its ability to generalize to new and unseen data. So in essence, hyperparameters matter because they determine the rhythm and harmony of a model's learning journey. Like tuning a musical instrument, we are searching for that perfect tone, that sweet spot where our model's performance shines the best. Remember, just as each song requires a unique melody, each dataset demands its own set of hyperparameters. The art of hyperparameter tuning lies in finding the symphonic blend that transforms a model from mere machinery into a best performer. Now that we have grasped the significance of hyperparameters, let's journey deeper into the strategies that allow us to uncover these hidden gems and sculpt our models into their best versions. But hold on, hyperparameter tuning isn't just a walk in the park. It's more like a puzzle with so many different pieces. If you change one hyperparameter, it might affect the others. And finding the right values can be time consuming and resource intensive. To make things simpler, hyperparameters can be like the gears in a clock. Tinkering with one can set off a chain reaction affecting how the others in the clock behave. It's like adjusting the speed of one gear in a clock and finding that it impacts the timing of all the other gears. Now, one main consideration to consider when talking about hyperparameter tuning is called the curse of dimensionality. The curse of dimensionality is like exploring a vast forest with countless paths, each representing a different combination of these hyperparameters. The more dimensions you have, the more intricate and challenging the journey becomes. And let's not forget the resources required for this. Hyperparameter tuning demands computational power, time, and patience. It's like embarking on a long hike through the wilderness, requiring preparation, determination, and perseverance. But as with any problem, this too has its silver lining. To address the problems of dimensional reduction, practitioners often use various techniques such as domain knowledge, dimensionality reduction, sequential approaches, regularization techniques, or even ensemble methods. Now that we have a good understanding of hyperparameters and the different challenges that they possess, let's dive into the different strategies that are used to perform hyperparameter tuning. Think of these strategies as tools in your toolkit, each with its own unique approach to exploring the hyperparameter space. First up, we have the grid search method. Grid search is like methodically scanning through a map, marking every point as you come across. You define a grid of possible hyperparameter values and the algorithm tests each combination in the grid. The advantage? Grid search is exhaustive and guarantees you'll explore the entire specified search space. However, there's a drawback to this approach. It can be computationally expensive and time consuming, especially when dealing with many hyperparameters or a large search space. Next, we have the random search method. Random search is like exploring the map by randomly dropping pins. It doesn't meticulously cover every point, but it offers a good chance of stumbling upon promising regions. Random search is often more efficient than grid search, as it uses fewer resources while still exploring a diverse set of hyperparameters. Now let's talk about Bayesian optimization. Bayesian optimization is like having an intelligent assistant who learns from each step that you take. It builds a probabilistic model of the function that relates hyperparameters to model performance and makes informed guesses about where to explore next. Bayesian optimization is efficient because it adapts its exploration based on previous results, focusing on areas to yield better performance. These libraries not only saves you time, but often outperform manual strategies in finding optimal hyperparameters. Remember, there is no one-size-fits-all strategy. The choice depends on your resources, the problem complexity, and your willingness to experiment. Each strategy has its own strength and weakness, but they all share a common goal: to guide you toward the treasure trove of hyperparameters that unlock your model's full potential. Alright, now that we have talked about different strategies and concepts, let's look at how to perform hyperparameter tuning using Python library and a scanner library. So for this I am going to use a breast cancer classification dataset and explain how to perform hyperparameter tuning on it. You can find the same code in my GitHub profile that I'll be linking in the description down below.
Okay, so in this first code we import the required libraries, then we load the breast cancer dataset, then we separate the data and the target variables, and then we split the data into training and testing dataset. Now here I'm only using a fraction of the entire dataset to save time. You can skip this set and use the entire dataset. Then I'm defining the SVM classifier. We then define the hyperparameter grids for both grid search CV and random search CV and perform searches using both grid search CV and random search CV separately. Then finally, we print out the best hyperparameter and corresponding scores. So as we can see, for this we get same scores for both the search methods. And this is how we basically implement grid search CV and randomized search CV to perform hyperparameter tuning.
Now before we wrap up, here's a small piece of advice. Hyperparameter tuning is a journey and not a destination. So don't be discouraged by the trial and error processes. It's all about refining and improving your model, as hyperparameter tuning is a secret sauce that elevates your machine learning models from good to great. If you find this video helpful, give it a thumbs up and subscribe for more content on mastering the world of machine learning. Make sure to follow me on my social media handles to stay updated for more interesting content. Thanks for watching and see you in the next video.